Go ahead, Ryan.
No.
Okay, so today's goal is to finish chapter 14. We have been studying the concepts of equilibrium, and we have a little bit of content left. We have at least one more example of solving equilibrium problems, picking up with where we left off class last time. And then we have an entirely new concept to cover at the tail end of class. I will also briefly discuss the exam, which is coming up next week, and that'll be the next time you see me will be for the exam. All right, and I have a review sheet, review content ready for you to get you ready for that as well. Right? But if you remember last class, we were looking at these examples of problems related to equilibrium, and they fall into two categories. All right, that's our first divisor, is that we can either find an equilibrium constant, find a KEQ. It could be KC or KP, doesn't matter. Or we can find the conditions at equilibrium. That's as simple as that. All right, that's the first distinction between the two categories of problems. And then in each of those categories, there are really two versions. A problem where you're really just looking at all the equilibrium conditions tied together. All right, and so you're really finding the one missing piece. All right, that's the easier version. Or you're given information about where this system began, what its initial conditions were, and then you're asked about something at equilibrium, either the equilibrium constant or the conditions at equilibrium. All right, and so again, that's a pretty clear distinction as to which category you're in. If the initial conditions are mentioned at all, you're in that sort of more advanced case, and you're using a reaction table. Always, always, always with those problems. All right? So I'm trying to systematically help you figure out how to get started and how to approach all the possible problems that you could be faced with. And those two questions really are what you want to ask yourself. Am I looking for K, or am I looking for a condition? And then, am I only dealing with equilibrium, or do I have initial information and I'm worried about equilibrium? Okay, and that's all you need to set you on the right path. Okay, so let's do another problem that follows up where we left off class with these reaction tables. So our new reaction to work with is 2 hydrogen sulfide, 2H2S gas, in equilibrium with 2 hydrogen, H2 gas, and sulfur, S2. The equilibrium constant for this reaction is 1.08 times 10 to the negative 7. All right. If we place 0.8 molar H2S into a vessel and allow it to equilibrate, what concentration, okay, or rather what will be, let's say, the concentration of each species at equilibrium? So this is a category 2, sort of the more advanced version of the problem. How do I get that? I'm asked what will be the concentration. That's the question right there. So that's a condition, right? I'm not asked about the equilibrium constant. And I'm told we place, right? That sounds like the beginning. We started with this amount of stuff, and now we're asked about this equilibrium condition. So you see how I'm applying those two principles that I just spent a minute outlining. Okay. Anytime we find ourselves in that boat, we want to set up an equilibrium table. So I'm going to rewrite my reaction here. And my equilibrium table consists of these 3 rows of information. Initial concentration, the change in the concentration, and the equilibrium concentration of each of our chemicals that are present. All right? Our first row comes from the numbers provided in the problem. So we're told 0.8 molar for H2S. Neither H2 or S2 is mentioned. So the only way this problem is fair, literally, is if they are 0. Okay, we have to have a number for them, so they have to be 0 since no number is provided. Okay. Now, in some of the problems last class, we were given a little bit more information that told us something about one of our chemicals at equilibrium, and that let us fill in the rest of the table. All right, but we're not given any other quantities for what's happening here in equilibrium. All right. So this is going to be a case where we need to conceptually introduce a variable to represent some of the reactant, reacting over to the product side. Okay. We don't know how much yet, and that's what we're really trying to find. So we're going to use a variable, an x, to stand for that amount. And instead of putting x here, I'm actually going to put 2x because I want to match the coefficient ratios. If I put x, that would be okay. I could put plus x for hydrogen, but then I would have to put plus 1/2 x for sulfur, and I'm not interested in the fractions. So it's just a lot easier when you're using a variable to automatically have them, in terms of x, match the coefficients in the reaction here. All right? So we should be all set for now. Again, our opposite sides have to have opposite signs. Okay, and I thought a little bit more about the question that we had last class about how do we know this has to be negative? Actually, there's this beautiful thing that would happen here. Even if we guessed wrong and put plus here and minus here, we weren't paying attention to the idea that these numbers have to get bigger. The math, when we solved it out, like the quadratic formula or something, would give us a negative answer as the reasonable answer. The negative of that negative would prove that this side is positive and has increased. So you can even make that mistake. As long as you do your algebra all correctly, it will catch it for you, which is a really nice feature of these reaction tables. Okay? But it is a little bit less confusing if you think about that ahead of time. All right, so now we just work down. If I follow again what we did the other day, this was really our first step, by the way, introducing this variable. That led to us determining the other values in that row. And then our third stage, right, was to come down each of these columns. So this will be 0.8 minus 2x. This will be 2x, and this will be x. The fourth stage in our problems the other day, when we used the reaction table, was to substitute our equilibrium values into our equilibrium constant expression. So that would be the hydrogen concentration squared times the sulfur concentration divided by the square of the hydrogen sulfide concentration. Okay. So if I put my numbers in now, I have 1.08 times 10 to the minus 7. Okay. Are we still recording there? Just checking, just making sure. All right, so I'm going to check on that a few times here. And this expression is going to get a little bit messier than the one we had last class, unfortunately. All right, so we would put in 2x for hydrogen, and then that needs squared, times x for sulfur, divided by 0.8 minus 2x, and that needs to be squared for the hydrogen sulfide. Okay. Now last example, we ended up with a quadratic equation, an x squared. This is going to be an x cubed in the numerator, I could tell right away, because I'll square this piece first, 4x squared, then multiply it by another x. Then our denominator is going to be 0.64 minus 3.2x plus 4x squared. And ultimately, when I do all the shuffling, this is going to equal 0, when I isolate everything on one side, is equal to 4x cubed minus 4.32 times 10 to the minus 7 times x squared, all right, plus 3.46 times 10 to the minus 7 times x minus 6.91 times 10 to the minus 8. Potentially, there are 3 solutions now, right? An x squared equation has 2 solutions, 2 roots. An x cubed has potentially 3 roots, depending on its shape. Uh-oh. This is not getting any better than what we had last class, that's for sure. All right. And this would be really challenging to solve, I'll be honest. All right. The quadratic formula can't help us because the quadratic formula is only good for an x squared formula, okay, or equation, right? There is no analogous formula for a cubic equation where you can plug in the A, B, C, and D in this case. Doesn't exist. All right. So what are we to do? How are we to get the answers that we need for our problem over here? All right. Well, if you had a graphing calculator, you could use the graphing calculator to solve for the roots here. A lot of graphing calculators do that. All right. I see a lot of them around the room, luckily. Okay. But you don't have to have one of those for this class. All right. And I prefer not to do that either. Okay. The reason we got into this mess here, or maybe I should take a different approach. We can avoid this entire mess, actually, if we stop and think a little bit about the chemistry that's being described in this reaction here. All right, and this is something we want to learn. This is really a quintessential lesson that we want to learn to move forward with all equilibrium problems. Okay, so before we do any of this math moving forward, okay, so before we set up our reaction table, we should consider the size of our equilibrium constant. The size of our KEQ. One of the first days that we covered equilibrium in this chapter, I divided equilibrium constants on a numerical scale into 2 halves. Does anybody remember roughly what they were? An equilibrium constant can be either or, right, large or small, right? And there was a difference between the meaning of those things. Our large equilibrium constants are ones that they mean the system loves its product side. It takes its reactants, in other words, and successfully moves them over to the product side. But a small equilibrium constant is a system that loves its reactant side, and it lives over here. So if you start with a whole bunch of your reactants, you end with a whole bunch of reactants, and it looks like nothing really happened. Okay? Right. So I've done the silly eraser analogy thing, right? With the pile of erasers and we move some over there. Okay? So imagine we came in and had a pile of 800 erasers here waiting as our reactants. But only 1 or 2 of them moved over to that side. Okay? That's going to be a very small equilibrium constant. And you know, if I made you close your eyes while I moved the 1 or 2 erasers over and then you reopened them, would you honestly be able to tell the difference between 800 and 798 erasers here? No. And I said, well, how many are there? You'd say it's still pretty much 800, right? Okay. So that is the justification for us to make a simplification in this problem here. All right? Anytime we have a really tiny, I hope you agree, this is a really tiny equilibrium constant, 10 to the negative 7, okay? The amount of reactants that we lose is going to be basically undiscernible from what we're starting with. You just told me you wouldn't be able to tell the difference between the 798 and the 800, okay? All right? And so it's gonna be worth our while, so to speak, to approximate this number as still being 0.8, is what it started out as, okay? And that number is the source of our problem. That 0.8 minus 2x is what led to this right here, which is what led to these ugly terms in the middle of this problem right here. So by justifying a reason, coming up with a reason to ignore that, we're going to make the math a whole lot easier. All right. We're still going to get a really, really accurate, close to the true answer. I'll show you I'll share that with you in the end. Okay. So now we're going to put all that down. So before we even start, we want to look at the size of our equilibrium constant. When Kc is very small, okay, for our purposes, that means, Keq, this should be when Keq is very small. So for our purposes, that's pretty much any time your equilibrium constant is going to be 10 to the negative 4 or smaller. Okay, that's the very small category. All right. The amount of reactants that actually move to the product side will be so small that we can ignore its loss. That we can ignore its loss relative to the initial amount of reactants. In other words, what we're saying is that the equilibrium amount of our reactant is pretty much approximately still going to be equal to whatever the initial amount of reactants were. Okay? And this, using this in the reaction table, is known as the approximation method. Now I get the magic of just erasing the work that I did here. You might want to rewrite the entire table again. Okay. So we would set up our reaction table again, but this time the thing that's going to be different is in the bottom row, I'm going to say that this is approximately still just 0.8. Instead of the 0.8 minus 2x. Now another important piece of this idea here, this approximation idea, I cannot ignore the 2x and the x on the right side. Okay? Yeah, we might not notice our pile of erasers going from 800 to 798. But would the student over here notice their pile going from 0 to 2? Yeah, okay. Relative to nothing, even the tiniest amount is going to be noticeable. Okay? And so that's again the distinction. It's all about relative. When you're comparing these extremely tiny changes to a big starting amount here, that's where you can ignore them. But compared to 0, no, you've got to keep that number there. Okay? So these numbers now would go into our equilibrium table, or our equilibrium constant expression. 2x would get squared times x. That's the same as what it was before, but now our denominator is just 0.8 squared. So we still get a 4x cubed in the numerator divided by a 0.64 now in the denominator. All those middle terms are gone. This just becomes 4x cubed equals 6.91 times 10 to the minus 8. So we divide by 4. X cubed is 1.728 times 10 to the minus 8. And then we take the square root. X is 0.00259 molar. Okay. A lot easier to solve, I think. All right. Okay. Now, you'll still have the, be able to take cube roots, okay? You might have higher order powers, x to the fourth. That all is going to depend on the coefficients of your reaction, okay? But you should never, I've erased it already, I never need you to solve that ugly equation that I had. If you write one of those, you're being stubborn in trying to solve it, okay? I've got a different way for you to solve. If you get to something that looks like that, you've missed something that I've taught you, in other words. So you never have to solve one of those ugly equations. Quadratic, yeah, you could do the quadratic like we did in the last example. Okay? But you'll never need to solve out a cube with the middle terms or a fourth or anything like that. Now we're not quite done. The problem didn't just say find x, it said, well, what's the concentration of each species? So stage 5 now, after substituting stage 4 and solving, is to bring that value back into our table now. So sulfur will be 0.00259 molar. Hydrogen will be 2 times that, so 0.00518 molar. And I know I've written that H2S is approximately 0.8, but I'm going to actually go ahead and now be honest and figure out what it really is. Okay? I'm not going to say, oh, the pile looks like it's 800 still. I'm going to actually count it out. And so when I subtract the 2x, I will get 0.795 molar. Okay? Now this method is not without some error, right? Because we did make an approximation to simplify the math, right? The real value of x, if I had solved the cubic equation we had up earlier, would have been 0.00257. So it's really, really close, okay? And the smaller the k is, the closer the numbers become, actually, with the approximation method. All right, so for my time, boy, that was really worth it, okay? Especially when we think about significant figures, all right? Yeah, these two are a touch different, but this guy over here still would have been 795, all right? Regardless of how different the last position was there. Question?
You said the smaller k was more accurate.
Yeah, the smaller the k becomes, the closer this merges to becoming the real value, even when you use the approximation method there. Okay? All right. So again, the key is to start every problem now by looking for the equilibrium constant, if it's one of these category 2b problems at least. All right? And if it's a small equilibrium constant, you want to know that right up front so that you avoid the messy potential math that we have there. And so it's another distinction as you set up your work that I want you to look for. All right. So I've got a sheet here that has some additional examples of this, because this is a pretty challenging concept the first time we come through it here. But I didn't want to, just keep doing it over and over in class. So I've written out a few examples for you. side that's coming out face up has two examples about equilibrium problems. The first is similar to what we just did. It's another case of the approximation method being used. All right? The other side says LeChatelier's principle. That's not the side I'm looking at right now. I'm looking at the side that says a couple more equilibrium examples. Okay? So I would really like you to put these into your notes. Okay, rather than me taking the time to write them out on the board, I want you to add these into your notes. Don't just say, oh, I'll just read them. You literally, I could find gobs of data that state my case that you won't learn it as well if you just read it off this sheet of paper versus if you copy it into your notes on your own. Okay, so you could see roughly how much paper you need in your notes to do that. So if I'm sitting there with my notebook, I'm going to leave a full page essentially, or more maybe if you write bigger than 11-point Calibri font in your notes. And then you'll add these into your notes, okay? And of course, what you could see is the red sort of shows you my logic, what I would orally be explaining as we set up the problem and work through it there. The bottom one's a neat case. It looks like we're out of luck because we can't use the approximation method. It's got a larger equilibrium constant, 4.4. But when we set it up, you read through this, we get a special mathematical case where the right side of our expression here is a perfect square in the numerator and a perfect square in the denominator. And you can simply take the square root to get rid of the x squared that's there. But you have to take the square root of both sides in doing that. So it doesn't happen that often, but depending on what the coefficients are, again, sometimes you sort of luck into other methods to simplify the math that you're going to encounter in these equilibrium systems. All right? Okay. So I hope you'll add those two to your notes. All right, that leaves us with one topic left in this chapter. Fairly important in that it's, again, while we're being introduced to it in the general concept of equilibrium right now, it's going to come back in another chapter or two and play an important role when we look at some of the specific categories of equilibrium, in particular acid-base chemistry. That's where we're headed in our next chapter after we take our exam next week. Okay? All right. And this topic is known as LeChatelier's principle, or LeChatelier's, a more sort of American way, I guess, to say this French name. Okay? That's Chatelier apostrophe S, LeChatelier. Okay? So LeChatelier's principle explains how reaction systems at equilibrium behave when they are what we say disturbed by some external change. Okay? So a reaction system reaches its equilibrium point. Right? That's its goal. It's guiding, sort of North Star, if you want. We use that compass analogy when we talked about reaction quotients. They guide us to the equilibrium constant, right? But what happens if something messes that balance up? We've achieved a nice product to reactant ratio, what we want, and then something else comes in and ruins that for us. Okay? LeChatelier's principle tells us how to figure out what happens. Okay, and the principle is pretty basic. It says that a reaction system will shift itself in order to count videos. Okay, so again, a reaction system will shift itself in order to counteract, oppose, another word to use there, any stress, disturbance, change, okay, applied to it. It's attempting, or it will attempt, to return to the same equilibrium position if possible. Right? That equilibrium ratio, products to reactants, that's where the system wants to live. Okay, so it's going to try to get back to that if possible. Right? Now there are lots of ways we could stress or disturb a system. Okay? But to make life a little bit easier as we're learning about this, we're only going to consider the effects of two types of changes. Concentration changes and temperature changes. Okay? These will be the two categories of equilibrium stresses that we look at. All right. You can do things like pressure. You can do things like side ionic concentrations, but we're not going to worry about any of those things, fancier things. We're just going to look at these two basic ones, all right, to get us started. Let me go back to the, I'm loving this eraser analogy that we've been using. So the eraser example. All right. And let's go through those numbers again. We had me, and then we had our student. And we started with 6, 0, 5, 1, 4, 2, 3, 3, 2, 4, 2, 4. And that's when we were at equilibrium. Okay? And we had our Q, right, which was 0, 0.2, 0.5, 1, 2, 2. And so this is when we know we were at equilibrium, when the Q stopped changing and it became the equilibrium constant. Okay? So our eraser system has achieved equilibrium. Doesn't mean it stopped, remember. The student and I were still constantly exchanging erasers, right? We were just keeping our respective piles the same size. So here's how the disturbance could play itself out. We're at equilibrium. What if somebody added, let's say, 6 new erasers to my pile? So my pile jumped from 2 up to 8. Are we at equilibrium now? No. And what proves it is if we try to calculate Q. Right? Oh, back to 0.5. So we could forget about actually this LeChatelier's principle for a second. We already know about reaction quotient. Reaction quotient tells us what's going to happen now. Our reaction quotient is smaller than our equilibrium constant. Anytime that's true, we know the forward reaction is what's going to occur to get us back to equilibrium. So what's going to happen is we're going to start shuffling this increase in my pile over to the other side. So, if I go down to 6, the other side goes up to 6. Now we're at 1. If I go down to 4, the other side goes up to 8. We're back to equilibrium now. And that's where we would stay unless another disturbance happened. Okay? All right. So this is really demonstrating the LeChatelier's principle. The stress was to increase what we're going to call the reactants. My erasers are reactants. The student's erasers are products. Okay? And the counteracting was to then decrease my pile. All right? It was artificially or temporarily increased. So to counteract that, we brought my pile down, which consequently brought the student's pile up. All right? But the goal was to get back to the same ratio. Yeah, our two numbers are different than what they originally were, but they're in the same ratio that we had originally for our equilibrium constant. All right? So the net effect, sort of the lesson that we learned from here, is that any time a species has its amount, I can't say concentration because it could be pressure as well. So anytime a species, a chemical, has its amount increased, okay, the reaction system will attempt to decrease that species. This will cause the other species to experience changes as well. Okay. In this simple example, the other species went up. I don't want to change my eraser example too much, but if I had to take not just an eraser, but a piece of chalk, right? The pile of chalk that I would have to get decreased as well. And if I didn't add extra chalk when I added extra erasers, the poor pile of chalk's really going to suffer, right? Because it was already at its desired equilibrium amount, and now we're going to lower it even further because we added more erasers. Okay, so it's really going to unbalance the whole system, and everything's going to have to shuffle. All right, that's a little more advanced version of it. Okay, now. So another way of saying this, another language we might use for this, is that the system shifted away from the chemical that we added. We added reactant and the system shifted away or towards the products. That's the counteraction, to use up the extra amount that we added. Okay. Now sometimes we take stuff out of our equilibrium systems. Let's say, I've gotten back to this 4:8 ratio, and now I'm kind of running out of room here, so let me erase one line. But, let's say I remove the 6 and drop this back down to 2. Again, I'm not at equilibrium, right? Okay. Now, I'm at 4:2, and my KEQ is, is too small, so I know I need to move 2 more over to get back to my KEQ value of 2. So again, the Q became too small, and now it caused the forward reaction to occur. All right. But look what happened here. When we took something away, the system shifted towards it. Right? The system came to its rescue, you might say. Right? We took away some student erasers, so the system says, hey, let's make some more student erasers. Let's counteract what some external factor caused to happen here. All right? It's always the goal, counteract.
When you talk about shifting away and shifting towards, do you mean the part in which it was added to?
Yes.
Okay.
So we added it to the reactant in the original case, and we shifted away from that side, okay, of the reaction, from the reactant side. Here we took it away, we took away from the product side, and we've shifted toward the product, okay. In each case, it's subtle, but in each case, it's the counteraction, sort of the opposite effect that we have there, okay.
In measuring, similar questions are asking if it shifts right or left. Is that just the same thing?
Same thing. You just have to rethink. If we shift toward the products, that's right. If we shift away from the reactants, that's also right. Okay? There's just different ways of saying the same thing. Here, shift away from the reactants means you're moving towards the products, right? I could say it either way. Sorry that the English language gives us multiple ways to express the same idea, unfortunately. But yeah, and I'm going to show you in the back of the sheet that I handed out several different ways the question can get asked, so you get used to thinking in all the different ways rather than just one way of answering it. Okay? All right, so let me fill in this last piece that we have here. When we remove a species, the system will shift towards it. To try to replace some, it won't replace all, but some of the lost species. Okay, that's important. In both of these examples, first case, I added 6. In the end, I did not shift all 6 over to the other side, right? I only shifted 4 of the 6 to the product side. And then when I took 6 away, all right, I didn't shift 6 in response. I only shifted 2 that time, okay? So it's all about the ratio. So both of these are guided by concentration changes. We return to the same KEQ. And that's how we know when the system will stop when it gets back to KEQ. All right. The other type of change that we're going to look at are temperature changes for reactions, and they're a totally different animal. So let's consider them. To understand the effect of a temperature change, right away there's a big difference. We need to know the sign of delta H reaction. We need to know whether the reaction is endothermic or exothermic, because that's telling us how energy plays a role in this chemical reaction that we're looking at. And energy, of course, is connected to temperature. So to understand temperature, you need to know about energy in your reaction. And there are 2 things. It could be a product or it could be a reactant, exothermic or endothermic. All right. So this actually is going to give us 4 possibilities, 4 categories. And I like to divide them into just a big grid here. It's a big 2x2 table here. Across the top, let's put a temperature increase versus a temperature decrease. And the top row will be delta H greater than 0, so an endothermic reaction. And the bottom row will be the case of delta H less than 0. That's our exothermic reaction. Now let's define a generic reaction, like A plus B in equilibrium with C. So really, that means the top row, we can think of it as A plus B plus energy are in equilibrium with C. That's the way I like to think about it. When your reaction is endothermic, energy is part of the reactants. It's there to drive the reactants over there to that product side. On the other hand, the exothermic reactions are like A plus B in equilibrium with C and energy. So the energy is over there on the product side of the reaction. And when we think about it that way, we can, to some extent, use the lesson from the concentration changes to help us figure out what's going to happen. All right? There's a lot of dominoes that have to fall, though. All right? So let's get ready to figure out the different steps that happen here. So if we increase the temperature of this endothermic reaction, if we increase the temperature and we add energy, we've increased the ability to do this reaction, to do the forward reaction. Okay? So the temperature increase increases the rate of the forward reaction. Well, what's that do? The forward reaction then is going to increase the amount of products. And as we consume the reactants A and B, because now we have more energy. Remember those reaction coordinate diagrams? We can push more of our A and B over to that product side. We're going to decrease the amount of reactants. In the shift language, hope that came through pretty clearly, the shift language on the video, all right, we have shifted the system right away from the energy that we added. Okay, so saying the same thing, okay, but using different language to do so. Right? This is going to break the equilibrium constant, though. Right? Our equilibrium constant for this is going to be our product amounts divided by our reactant amounts. And we've just figured out that the products are going to increase and the reactants are going to decrease. So this fraction that we're calculating over here, this ratio, is not going to be the same number anymore. How is the new number going to compare? Is it going to be bigger or is it going to be smaller? It's going to be bigger, right? So the big picture lesson of a temperature increase for an endothermic reaction is you make it more product favored, higher equilibrium constant for it. Anybody ever grown cell cultures like an auger or something like that? You generally put those in an incubator, right? Have you ever done an experiment? I don't know if they do the experiment this way or have you do it, where you leave a plate out of the incubator and one plate in the incubator to see the difference or whatever? Okay? So not only will the plate in the incubator go faster, that's a kinetics situation. We know that temperature makes all things faster. But it will also go farther, meaning you'll get more. So even if you leave the plate out of the incubator for extra days, 3 days, 4 days, 5 days, you'll never get as much on that plate as the plate that goes in the incubator. Because that process is essentially is an endothermic process. And you're going to push it further to the product side, grow more stuff in the end, all right, than if you left it out. That's one of the reasons you do that. Okay? It's also the reason when we don't want stuff to grow that we decrease its temperature. All right? We're going to go in the opposite direction now. So when we decrease the temperature, this is a little bit different again, but in the shift language, what we've done is we've taken away the ability to do the forward reaction. But we haven't impeded the reverse reaction yet. So I don't know if you've ever been in a car driving down the highway and you're next to another car and then maybe you or the other car brakes all of a sudden because there's like a police officer or something, right? Okay? All of a sudden this other car, it's still going the same speed, but it looks a lot faster than you if you're the one who slowed down. Okay? So we have two reactions going the same speed. When we turn the temperature down, all of a sudden the forward reaction breaks, slows down, B-R-A-K-E-S. Okay, let's put the brakes on. But the reverse reaction, I'm still going at the same speed. So temporarily it's going to mess up the balance of the piles that we have again. All right? So when we turn the temperature down on our endothermic reaction, we slow down the forward reaction now instead of speeding it up. Okay? So the reverse reaction appears faster. What does that mean? That means that we're going to end up increasing the reactant amounts and decreasing the product amounts. So now our numerator gets smaller and our denominator gets bigger, so our equilibrium constant decreases. All right? And we've made the system more reactant favored. We've shifted it left. Okay? The reverse reaction is the favorable reaction at this time. All right? Those are three different ways we can say that same outcome. All right? Any questions on that? All right, let's look at exothermic reactions now. Pretty much everything just flip-flops, okay? Exothermic case, our energy is now on the product side. So if we increase the temperature, we're not increasing the ability to do the forward reaction, we're increasing the ability to do the reverse reaction, okay? So now our two cars are going along, and all of a sudden one of them does speed up. It's not that one has slowed down. Adding temperature allows the one reaction to speed up. And it's the reverse reaction, okay? Reverse reaction speeds up, or I guess we could say increase the rate of the reverse reaction, but okay. What that means is we're going to increase the amount of reactants, because that's what the reverse reaction does. It makes reactants. Okay, so we're going to end up increasing the amount of reactants at the expense of the products, decreasing the amount of the products. And we're going to see a decrease in KEQ. So the system is now more reactant favored. All right. So reactions that are exothermic, we often try to put them in a cool environment then. Right? Otherwise, they're going to sort of kill themselves off. All right? They're going to die out. And that's the origin of using a cooling system, for example, in your car. Your car has this extremely exothermic reaction when octane combines with oxygen to produce carbon dioxide and water vapor. Right? And a whole lot of energy. If that energy is just left sitting here, the temperature builds up, builds up, builds up. And it's going to decrease the amount of the forward reaction that can happen. So your engine will be less efficient then. It won't want to convert every octane molecule into carbon dioxide and water. So what do? Put a cooling system in, you pump that energy away. You take it away and you trick the reaction into happening more efficiently by cooling it down, in other words. All right? So you'd be in this box here. Temperature decrease. So now what happens when we decrease the temperature is we slow down the reverse reaction, because again energy is used in the reverse reaction. So the forward reaction appears faster. Okay. What does that mean? That we're going to increase the amount of products, decrease the amount of reactants, and when that happens, we see a net KEQ increase. So cooling exothermic reactions will give you a more product-favored outcome. And you get more, if that's what you're trying to make, your products, you get more by cooling the system down. All right, let's try to put this into a sort of a real example now, some practical consideration here. We've seen this reaction before when we were studying heterogeneous equilibria and writing their constants. So calcium carbonate in equilibrium with calcium oxide solid and carbon dioxide gas. What I need to add now is a new piece of information. What is the delta H of this reaction? So it's positive 174 kilojoules. So it's an endothermic reaction. All right? I'm going to ask a few questions to model the sort of the different ways that they can be asked. All right. And again, mastering, which we heard somebody ask about, asks them really in just one way. All right. But there are multiple ways you could really ask the same question. All right. So how will the pressure of CO2 change if we increase the temperature? Okay. Now, a different way of asking that exact same question would be, which side becomes more favored if we increase the temperature? It really is the same question, to be honest, all right? Or how does the system shift, meaning left or right, if we increase the temperature? They're all really the same question, okay? All right? Another question, let's say, how will, what did I do last, trying to remember the way I asked it last class so that it comes across as a different question. All right. Yeah. Oh, yeah, that's what I'm going to do. Which side, okay, becomes favored if we add some CO2 to the system? Okay, so there's a question where we're looking at the sides rather than a specific chemical. Okay. And what happens, that's the most general way rather than sort of, pushing you into a particular line of thinking, like which side or what chemical. Let's just say more generally, what happens if we add some CaCO3 to the system? Poorly spaced my writing, sorry. All right, so first question, how's the amount, the pressure of carbon dioxide going to change if we increase the temperature? So this reaction is endothermic, first thing I want to think about. Temperature increase drives the forward reaction, okay? So the temperature increase favors, we would say, the forward reaction. The result of favoring as the forward reaction is we're going to increase the amount of the products, one of which is CO2. Therefore, the pressure of CO2 will increase. That's the domino effect, right? Okay. That's essentially this box right here. All right. We raise the temperature, we're going to speed up the forward part of the reaction here. The forward reaction makes the carbon dioxide, the product, and therefore we're going to have more carbon dioxide, and naturally its pressure is going to be higher. Okay. Second question, which side becomes favored if we add some CO2? Well, CO2 is a product. So if we add some CO2, we're going to shift away from it. Right? Because all of a sudden our pile of carbon dioxide is too big. All right? And we want to bring it back down. So to try to decrease the carbon dioxide, we're going to shift away from it, which means the reactant side is favored or becomes favored. Shifts left in the language that I think the Mastering Chem question is going to ask you. All right? So this system now would shift left temporarily to take care of that extra CO2. Right? Last one, what happens if we add some CaCO3? Well, we could start to set down the same path that we did in this previous one. CaCO3 is a reactant, so we should shift away from it. But CaCO3 is a solid. Right? The equilibrium constant for this reaction, Kc, does not rely on that. Remember, we learned to ignore solids and liquids in writing the equilibrium constant? We ignore them and their effect on equilibria then altogether. And so what happens if we add some CaCO3? No change. No effect on the equilibrium, actually. The only way it would change is if we took all of it away. Okay? If we took all of the calcium carbonate away, then the system would completely throw the brakes on and turn left and start to make some calcium carbonate. Okay? All right. So, not sure where that cut off, but what we're saying is that solids just get ignored, liquids too. So if you had water, for example, it's the most common liquid in a reaction, it's really a trick question. Changing the amount of water, no effect on your system. Not true if water's a gas, so you do have to pay attention to what phase it's in. All right. So now the back side of the sheet that I've handed out has some additional LeChatelier's principle examples. And what I've done is considered 4 changes, the exact same 4 changes, and asked the question 3 different ways, or asked 3 different questions about this, again, to demonstrate the different way we can do this. So describe how the system is affected. That's kind of the way mastering's asking you to do your homework. Shift left, shift right, or unaffected. Okay? Or I could have said, well, how is the equilibrium constant? None of these were the equilibrium constant. If we came back and did that, this would have an increase in the equilibrium constant, and then these two would have no change on the equilibrium constant because their concentration changes. All right, so that's kind of a boring question. And then the third one, well, how is the concentration of one particular chemical affected? That's kind of like what we did here in this first one. All right, so there's different ways of asking the questions, but this, considering the exact same changes each time, I think will help you sort of cement those into place. And it won't matter which way the question is asked, you'll sort of adapt or adopt a way of thinking about what happens, and then you'll be able to answer any of the questions that we have. Okay? And so then that wraps up everything for chapter 14 that is going to be on the exam. All right. Now, I have a review sheet prepared for you, since you won't see me again until the exam. So just as I've done for the other exams, with the other exam for Gen Chem 2 here, this sort of lays out what's on the exam, what the material is that we've covered in these 2 chapters, and then there are a whole bunch of practice problems for you to look at and to go ahead and get ready for the exam. You want to go ahead and turn the video off actually for me, and then I've got 1 or 2 other things to say to Gen Chem students that are different than the other class. Bye.